Okay, uh, we're going to talk about Newton's law of universal gravitation. Basically, what he said is there is a directly proportional relationship between the gravitational force between two objects and their masses. So this force of gravity, Fg, which we know as weight, Fg is proportional, this little line means proportional to mass 1 and mass 2. Simple enough. There's some proportionality between the force of gravity between these two masses and the masses themselves. There's also, he also said that there's an inversely squared relationship between the gravitational force, the force of gravity, uh, and the distance that separates the two masses. There's some proportionality between the distance that separates, and it's a inversely squared proportionality, so 1 over, and call this distance between that separates them r for the radius that separates the two masses. And when you put these together, you get Newton's universal law of gravitation, which says that the force gravity between any two objects is equal to G, capital G, which is the gravitational constant times the mass of object 1, the mass of object 2, divided by radius squared. So G m1 times m2 over the radius squared. And G is equal to 6.67 times 10 to the negative 11th. And it has units of newtons times meters squared over kilograms squared. So this gravitational constant is always used in these calculations. Uh, and that was developed through experimentation. This is the gravitational constant, and this is the law of universal gravitation. So you have two masses, multiply them, divide by how close they are, and then multiply it by the gravitational constant. And I just realized I drew my proportionality symbol wrong. It's more like a fish, more like a backwards fish sign. Let's redraw it. Proportional. Proportional. Now let's try an example. Okay, we have the gravitational attraction between a 50 kilogram boulder and a rock is 2.58 times 10 to the negative 10th newtons, and the center to center distance is 20 centimeters between them. Compute the mass of the, let's change that to rock. Center to center distance is 20 centimeters between the boulder and rock. Okay, so we can figure this out because we have the gravitational attraction, the force of gravity, that's equal to 2.58 times 10 to the negative 10th. And we have the mass of the boulder. We're trying to figure out the mass of the rock. So force of gravity is equal to your gravitational constant times the mass of object 1, which is our boulder, times the mass of object 2, which is our rock, and dividing by the radius squared, which is the center to center distance between the two, which we have is 20 centimeters. We're going to have to compute that to, or convert that to meters, which divide by 100 gives you 0.2 meters. So plugging in our numbers, force of gravity is 2.58 times 10 to the negative 10th, which is equal to, plugging in 6.67 times 10, I'm sorry, this should be 10 to the negative 10th. Gravitational force is 6.67 times 10 to the negative 11th times, you got a 50 kilogram boulder, and mr, mass of the rock, is unknown. Over the radius is 0.2 squared. Okay, first thing I'm going to do is 50 divided by 0.2 squared. When you compute that, you get 1250. Bring everything else down. So you've got 1250 times your gravitational constant times the mass of the rock equals 2.58 times 10 to the negative 10th. Multiply these two numbers. When you multiply those two numbers, you get 8,337.5 times 10 to the negative 11th. Real easy way to multiply numbers. Just multiply the front number and bring down the power of 10. And then once you get down to the end, you can put it in correct form. So we can divide both sides by 8,337.5 times 10 to the negative 11th. Divide both sides. This one cancels out, and you're left with mr on one side. And do your division over here. And when you do the calculation, you get 0.000309 when you divide 2.58 by 8,337.5. The powers of 10, the 10 on the bottom comes up and becomes 10 to the negative 10 to the positive 11th, which leaves you with a 10 to the first power. And if we put this in correct form, we'd have 3.09 times 10 to the negative third kilograms for the mass of the rock, or 3.09 grams. When you get into planetary data, you're going to see different symbols. A lot of times when you're calculating gravity with planets, you'll see the planet represented with a capital M and a circle. If there's a cross in it, this stands for the mass of the Earth. Mass of the Sun is usually represented with this symbol. The circle with the dot represents the Sun. The circle with the cross represents the Earth. So this is Sun. And the mass of the Moon is often symbolized with the crescent moon shape. And you'll also see these symbols represented with their radius. You know, if you do radius of the Earth, you know, you'd still use this symbol. You'd use R, and that would signify the radius. If you wanted to do the radius between the Earth and the Sun, you'd have R with the Earth symbol and the Sun symbol. Same thing with Earth and Moon. There's a variety of things, and other planets have, you know, different symbols. So just be aware of that when you see them, and you know, don't feel like I want to expose you to it and make you understand that it's not a big deal. It's just a way uh, distinguishing between the planets' masses.